All right, so our next speaker now will be talking about something which is quite which is a bit more, I dare to say abstract, but it's at least as interesting. It's just as interesting as the other talks, just as interesting. We're going to be talking about Monte Carlo methods. And so in that sense, we're trying to understand what could be an empirical approach to solving certain, for example, risk analysis problems, also given that as of today, general purpose error-free quantum computing is not yet available. So for that, I welcome Mr. Sven Kerstan, who is head of research at JOS Quantum. Mr. Kerstan, welcome. The floor is yours.
Thank you very much for the introduction and for the invitation to speak. As we just heard, I'll talk about Monte Carlo simulations on noisy quantum computers, which is all we've got these days. Noisy quantum computers are quantum computers which cannot process information without making errors. And I'll start my story a year ago at last year's Bitkom Quantum Summit. I gave a talk, a quantum algorithm for the sensitivity analysis of business risks. If you've missed it and you're interested, it's available on YouTube, I believe. The key insights at the time were Monte Carlo simulations ported to a quantum computer did actually give a speed up for the simulation and also for what we did at the time, which was a sensitivity analysis of the model. And it actually took the calculation time from years to minutes. That was in simulation, of course, because, as I've said, the quantum computers that we have today are prone to noise, to errors, and that stops us. That's one of the things that stop us from actually doing this real-life size on real quantum hardware. What was really encouraging at the time was that we only required about 250 qubits to run the full-blown business application that they were doing there. So 250 qubits is really not very much. People who build hardware these days are almost there, maybe next year. But since then, our focus has changed a little bit. So it's a year later now, and because it depends a lot on how you count quantum operations. The number can be a fair bit larger depending on what machine you look at, and but this is just to give you an idea. 100 million sounds reasonable, and it's absolutely out of the question to execute 100 million operations on a quantum computer without errors, and that's not just today; that's in the foreseeable future. So you might think that could be a singular case. It's a problem in this particular model, but we've encountered this same issue, really high gate counts, and other client projects as well that concern Monte Carlo simulations. So this is a generic problem. So even if you've got your sufficient amount destroyed by the hardware errors. So what can we do about that? And that's what this talk is going to about. So as you've been warned, this gets slightly more technical maybe. So you may have seen such a thing here, a quantum program depicted like this. This is what's called a phase estimation, and this is the thing that's underlying the quantum amplitude estimation, and that is just the word for the Monte Carlo simulation on a quantum computer. So here's a really simple and small scale model. You see these blocks on the left here. They basically prepare the quantum computer to do the simulation, if you like. The purple dots are the Monte Carlo simulation. And the black dots on the right, they are the measuring of the output. The output in this case is a number in binary encoding. And this number informs you, if you do a Monte Carlo simulation, about the likelihood of the events that you looked for. So you can use this as, well, there's quite a bit of literature about this for various purposes, such as value at risk application, maybe. So this, oh, sorry, I jumped. Oops, really wrong. Back to the circuit, I'm sorry. So in this case, we get an answer with 4-bit resolution. That's, of course, in practical terms, very little. You can distinguish 16 different types of outcomes. This has to be quite a bit larger, really. And the model that we're analyzing here has just 1 qubit, qubit 4 in this case, so it's really small. But this circuit really could be a quantum amplitude estimation circuit if we had this really simple 1 qubit model. And that's still a bit too complicated to see what's going on, so we make it even simpler. We just look at 2 qubits, Q0 and Q1 in this picture. And you can think of this as a part of the earlier circuit. I'll switch back for a moment. You see, you can think of the output here as coming in 4 chunks. The top level, Q0, the first, second, third qubit, and each of them receives feedback. It's called a kickback from these purple blocks here. And they contain the information we want about the statistical frequency of the events we're looking for. And this is done in 4 chunks. You see one kicks back 8 times to the 0th quantum wire, one kicks back 4 times to the first, and so on. You can do these 4 things in a sequence. So, for example, here is the thing you saw at the end of the diagram. You just do these 8 kickbacks, and then you write another quantum program which does just 4 kickbacks, and then one that does 2 kickbacks. And you combine the results on a classical computer at the end. That's actually very efficient. The Monte Carlo simulation then is still performed on this on the quantum computer, and you still have the theoretical advantage, the speed advantage of the quantum computer. You see these plus A's here. They are the information we want from the execution of our Monte Carlo run. That's how you can think about it. Each of these blocks is like one Monte Carlo run, only it's a quantum Monte Carlo run, and it gives you more information than a classical one. But the key is that on this qubit 0, we collect all the feedback that comes from the first quantum wire here. Each time you get a plus A here. So the key of the problem and the key of the solution is the additivity of these kickbacks. So each of these things kicks back a number plus A to the top quantum wire, or for the experts, to the 1 state in the quantum wire. The next one does the same, and they add up. So after executing 2, you have 2A. After executing the third one, you have 3A, and so on. So in the end, on this quantum wire, you'll have 8A. Now, that's the theory. That's if nothing goes wrong. So the question is, what happens when something does go wrong? Well, the first thing one needs to know is if the bit flips, that's one of the common errors, not the only possible error, but one common error, and that's the one we look at because it makes things nice and simple. It's going to change the state we've prepared in the beginning, the one that contains the information we want. And what we prepared here is called an eigenstate. Don't worry too much if you don't know what that means. The important thing is there are 2 such eigenstates, and that's always true, even for large complicated models. And in this particular case, an error flips the first eigenstate to the second eigenstate. Now, the bad thing about the second eigenstate is that if the system is in the second eigenstate and you perform a Monte Carlo simulation, you don't get plus A, you get minus A. So the real world large systems behave slightly differently. They behave worse, but we'll keep it simple. So let's forget about that, and let me just say that the solution that I'm going to present here at the end is going to take care even of the complicated cases. So we look at the same circuit, but this time there's an additional NOT gate here, which flips the qubit 1. It shouldn't be there. It's an error, maybe some cosmic ray hitting the quantum computer or something, thermal fluctuation. Anyway, we execute the first instance of our little quantum model. We get our kickback A. We do it again. We're at 2A now on the top wire, another one, 3A, and you get the picture, 4A, 5A, 6A. And now the error hits, and things start going wrong. I said we flip the state of the second, of Q1, the first qubit here now, to the other eigenstate, and the kickback now is minus A. Still accumulating, but now it accumulates the wrong value, minus A. So instead of the correct answer, 8A, we're left with 4A here on the top wire. That's quite wrong, of course. It's only half of what you want. Let's look at a second example. The error could have occurred. It's a random thing. These errors can, occur at any time, any place. It could have occurred after the fourth run. And if that had happened, the result would be even worse. We would have 4 plus A's and 4 minus A's, because, as I said, the state flips, and from there on, everything that follows goes wrong. So it looks like our model contains nothing at all. It's 0. You could, of course, after all, it's random, have 2 errors happening while you execute your program. And what happens is exactly as you would expect. You start with plus A, an error occurs. From there on, it's minus A's, another error occurs. It flips back to plus A's. So in this case, you get 2 A's. Thing is, you never know what you're going to get. So we can plot what's going to happen on average, because quantum computers, you're going to use typically more than once. You run the same program several times, and you see what's happening on average. Now, on average, if you have an error-free quantum computer, the theoretical thing, what you'll get is the blue line. For each run of the quantum Monte Carlo system, you'll get 1 kickback, 1 plus A, if you like. So you run it 10 times, you get a kickback of plus 10A. You run it 25 times, you get 25. So it's a straight line. Now, you can do the math and model what happens when you have these random errors. You have to say how frequent these errors are, of course. So let's assume you have a 10% error rate. So executing a model with a 10% probability yields an error. You get the purple line. So you see it sort of flattens out, making more runs at some point really doesn't really gain you much. The kickback sort of stays the same. If the error rate is higher, you get even lower values for the kickback. So this actually destroys pretty much all hope for executing these things on noisy quantum hardware, because the perfect signal that we would want is not what we get. We get a useless signal, something that we can't really combine to extract the information we want. And the higher the error rate, the worse things get. So the question is, what now? What can we do about this? And the answer is, roll this entire circle out and execute everything in parallel. So here I show you the same example that we had earlier, but instead of executing all these Monte Carlo runs on the same qubit, on Q1, one after another, I give a separate qubit to each of them. The first model is executed on Q1, the second one on Q2, the third one on Q3, and so on. So it's pretty much the same, and it works the same. So if I have an error here, I get my kickbacks as before. The first one gives me plus A, the second one as well, the third one as well, until I hit the 7th one here, which has a bit flip error, gives me minus A. So the sum is now only 6A. But the key thing is, it doesn't matter anymore where the error happens. So if I move the error to the 5th qubit, well, I get a minus in the 5th place, but what comes afterwards is still going to be a plus A. So I still get 6A. This actually changes the behavior qualitatively in a really important way. And you see that of the system, you get some fraction of 1 times of the kickback. So if you run it 20 times, you get maybe 16 kickbacks here. But that looks a lot better than the orange line, the purple line here. If you have 30% error, you get the purple line in the parallel case, the green line in the serial case, in the standard setup. And well, the key thing, as I said, is it's still linear, which means you can still use it. And this advantage, as you see, will grow bigger as well as the system gets bigger. For really small numbers of runs here, 5, 6, 7, 8, 9, the difference is not very big. You might not even notice that the usual serial execution is not like a straight, not behaving like a straight line. Full signal if we execute things in parallel, but a rather useless signal in a case of the serial execution. Which brings me to the conclusion. So if we have parallel circuits rather than serial circuits, that's certainly going to help with hardware errors. So in the case of quantum phase estimation, and therefore also quantum amplitude estimation, which is a special case of phase estimation, as I said, it gives you error resilience. So you still get errors, but the errors don't destroy your result completely anymore. And the same is true for the low depth versions of quantum phase estimation, quantum amplitude estimation, which are the more modern version of it, where you can leave out some parts of the circuit, chop up the circuit into individual circuits, each of which you can run, and then combine the results in classical post-processing. And what's really interesting, of course, is if the error is known, and you can know it by trying, how wrong does it get when I do a single run, how often does it execute correctly, then you can actually even adjust for the error that your machine makes, because it tells the error corresponds to the slope of the curve I told you earlier about. And if you know what the error rate is, you know what the slope is and what it should be, so you can correct your answers and get the correct result up to the precision that you know your error with. One thing I haven't mentioned yet, but well, it may sound obvious, the gate depth is going to be lower, because you can now execute everything in parallel. Current hardware is usually not able to do that yet, but in principle, and certainly it will be, you can execute each of these blocks at the same time. And that speeds up execution, of course. So if you go to something that starts being realistic, like an answer with 10-bit resolution, maybe, that means about 1,000 executions of the quantum Monte Carlo piece. Then if you do it in parallel, your program is going to be 1,000 times faster. And 1,000 times faster, of course, is nice, even though in terms of quantum speedups, it may not be that impressive. But it may still help with the decoherence problem, because, as you may have heard, some quantum computers don't stay, well, quantum computers in general don't stay in their coherent quantum state forever. They can only hold that state and therefore work on a calculation for a certain amount of time, which can be rather small. And then you have to be done. And if you're not, things go wrong as well. So being faster is a good thing. So we think one will be able to use quantum Monte Carlo simulations on noisy hardware, and we won't have to wait for generally error-corrected quantum computers. If you're interested in the full details of the story, there's a paper on the archive, and you can see the link here. And with that, I would like to finish. Thank you for your attention.
Mr. Kerstan, thank you so much. You finished just on time by the nanosecond. I'm very impressed. Thank you so much for this. We unfortunately don't have time for another question. However, you already pointed to the paper that is available on archive. So I think people would also be able to engage with the paper and then with you if they want to. Thank you so much for being with us today. All the best to you, and enjoy the rest of the conference.